Sure. So welcome everybody to this webinar and panel. I am Sandip Ray. I'm from the University of Florida, and I'll be moderating this panel. There are 5 very distinguished panelists here. I'm going to introduce the panelists very soon as we go into their remarks. But before I do that, I want to welcome Jin to talk a little bit about this CAD for assurance webinar series. So
Thanks. So Sandip, can you show that slide?
Yeah.
Yes. So welcome everyone. So for many of you, you are very familiar with these CAD for assurance webinars. So so far we have provided 6 webinars and 2 panels, and today is the 3rd panel. And the CAD for assurance is established in October 2020. So it's mainly supported by the University of Florida NELMS Institute, and also the IEEE CDA, IEEE Council for on Electronic Design Automation, and IEEE Hardware Security and Trusted Technical Committee. We also have technical supporters like Mercury, Northrop Grumman, Huntington Ingalls Industry. So far we have more than 4,000 unique visitors to the website and more than 16,000 page views. So this is a community we try to build so that all these CAD for assurance tools and the researchers can communicate with each other and can share their findings. This is our effort as hardware security researchers to mimic the software domain that they share the tool so that more and more people can try to use those tools and eventually adopt that in the industry beyond this academic work. And Sandip, please go to the next slide. So, okay, so it's not changing. So
it didn't.
Oh, here we go. So this is a brief overview of all the lists in this year. So you can find that either in the IEEE CDA website or on the cadforassurance.org website. So most of the webinar and the panels, we have the recording. And if you miss or your colleague want to watch those videos, so you can provide them this link. So in this year, we have a monthly events, and this event we will continue our effort in the coming years. So overall, these webinars and panels are very, very welcomed by the community. And we also hope those attendees, you are not just become the viewers, the attendee, but also become the contributor and deliver or share your tools through this website. And then through these webinars, you can also introduce those tools. So with that said, I hope all of you can enjoy today's panel. Sandip, so the podium is yours now.
Okay. So let me make a couple of very quick remarks to introduce the topic of today's panel. And then I want to have obviously most of the time in discussions and opinions of the panelists. So let me start with a very personal anecdote about this general problem. This problem has been very close to my own heart. So when a long time back, I will not tell you how long, but when I was I had just graduated and joined industry, had a lot of hair in my head. I was conversing with a security validator at Intel, and I asked this question: what is security validation, and what is security assessment, and what do you guys do? And what I'm showing here is kind of it's while not an exact quote, a close paraphrase of what he said. What he said was that you will need to review and assess the overall platform for attack opportunities which undermine security objectives in ways not covered by traditional approaches. And of course, at that time, I had no idea what he said, but over the years, I have marveled at how much he packed in these 4 lines. In particular, if you think about it, a platform involves, you'd have to look at more or less hardware, software, physical access, everything. If you have to look at attack opportunities, you'd have to think about all potential attacker motivations, entry points, and so on. If you are going to think about how they can undermine security objectives and where they come from, they can come from the features, they can come from the architectures, they can even come from the user's expectation, even if not explicitly defined. And then in ways not covered by traditional approaches, essentially meant that this security validator would have to think about all the other validation efforts and minimize duplication of efforts and find gaps in them. Seemed like an impossible task to me over the years as I pondered over these statements. But as we went over the last decade, and I lost more and more here, there were a couple of other things that happened as the problem evolved and escalated. And we hear at least 2 issues. One issue that we always hear now is the issue with complex supply chain. When we build an electronic system today, maybe somewhere in California, well, you get IPs from all over the world, you test, fabricate somewhere halfway down the globe, you test and do the assembly and testing at another continent. And at any point, of course, there can be a problem, a vulnerability introduced, whether maliciously or inadvertently, that can compromise the security and trustworthiness of the whole product. And then there is this other problem, which is what we call time to market shrinkage. It used to be that we would have about 3 to 4 years from exploration to production for a computing device, and it is getting shrinking and shrinking to probably targets less than a year now at this time. So all these things are happening, and the problem, of course, is becoming mind-boggling as we go. But in all of these approaches, it's also possible to lose sight of some of the fundamentals and so we need to ask ourselves this question. Okay, so did the problem fundamentally change? What exactly was the problem and how did it change? Are there new conceptual problems, new conceptual challenges? Will the verification and assessment tools that we have worked on for decades, will they work in the new era, or do we need to rethink? What is it? So that is the question in front of this panel. And this panel is a very distinguished set of panelists. We have Kevin Bush from MIT Lincoln Lab, Robert Jones from Intel, Sharad Malik from Princeton University, Janine Mckeown from AFRL, and Keith Rebello from Darpa. So what I'm going to do is introduce each panelist in turn and let them give a brief position statement or remarks on this problem. And then after that, it will be open microphone with Q&A from the audience. So I will start with Kevin Bush. Before I go on, as the panelists are going to give their opening statements and position statements, for the audience, please think about the questions that you want answered from these panelists, or anything that jogged your thought when you hear these, and type them in the chat. I'm going to look at the chat window and I'm going to read out the questions, and I might add some questions of my own as the panel goes. So now with the opening statements, Kevin Bush, he's the leader of the Cyber Physical Systems Group at MIT Lincoln Lab, which seeks to improve hardware security for the national security community. His group has expertise in side channel analysis, reverse engineering, counterfeit detection, Trojan prevention. He has served as a technology fellow on the Chief of Naval Operations Strategic Studies Group, as a computer scientist at Space and Naval Warfare Systems Center, and as a research engineer at the Institute of Computational Engineering and Sciences at University of Texas at Austin. So with that, I will let Kevin take the floor.
Thank you, Sandip. It's a pleasure to be invited to this. Thank you so much for the invitation. As it says in the slide, I do lead a cyber-physical systems group at MIT Lincoln Laboratory. A lot of folks ask what that means. It really means we focus on non-traditional methods of cyber access and effects. In particular, issues of hardware security fall under that bucket. So my group has been working on national security challenges of hardware security and microelectronics in particular for many years. This topic, the issue of security assessment and verification, resonates with me personally as someone who's been out evangelizing the problem of hardware vector attacks through most of my professional career. I'll start things off by saying security is hard, and hardware security verification is especially hard, not just because of the complexity of devices that we engineer, things like design complexity, scale, densities, production volumes, heterogeneity, IP reuse. These all are contributing factors, but also because it's important to remember that we face a thinking, breathing opponent, that advancements in attacks, especially physical probing, modification, SAT-based attacks against designs, et cetera, are raising the bar for the security verification community. So not only is the scale of the problem growing, but so is the threat. The good news is that the nation or the world actually is more or less awakening to this problem. Supply chain shortages over the last couple of years and headline grabbing news articles about major manufacturing deals and global supply chain issues have kind of raised public awareness to broader supply chain concerns. But similarly, and perhaps more importantly, there's been some recent and pretty seminal papers on design integrity attacks and defenses that have attracted, I think, a critical mass of expert awareness. So it's reassuring to me to see an increased focus on the problem. Overall, I think we have a tremendous need to measure and quantitatively demonstrate security progress. I think to do that, we kind of need three things. We need metrics to measure the attackability of designs. We need reference test designs against which the community can agree on how to evaluate the efficacy of certain techniques or tool capabilities. And we also need quite a bit of improved realism in the published threat models that take into account the gravity of the security consequences that are happening, as well as the trending sophistication of attacks. The problem space is huge, so there's a lot of opportunity here. As we all know, verifying that a device will function properly is hard enough. Verifying the negative, that it won't do what it's not supposed to do, is even harder. I think we all really intuitively understand that. But design integrity and confidentiality across all phases of a life cycle are going to be pillar challenges in the coming years. And similar challenges on the data side, the data which are microelectronics process, especially against physical attacks, will be critical to address. So with that, I think I'll just wrap up this intro, I think, with trying to call out or identify, forecast a few particularly hard problems that are going to be important to address moving forward that perhaps haven't been the focus in the past. So the first is design time mitigations against runtime or physical attacks. What can I do at design to prevent a runtime failure of a security property? Two, anticipating security vulnerabilities that might emerge from the composition of separately designed, still integrated components. The absolute hockey stick of third-party IP integration certainly raises concern here. And third, this issue of balancing or holistically integrating solutions that are software visible, architectural, micro-architectural, or transparent, and constrained to EDA tools, and having a holistic approach that balances those three, I think, is going to be another important challenge moving forward. So with that, I'll kind of get off the stage for now, and thank you.
Thank you, Kevin. That was a great set of points. Our next panelist is Robert Jones, and Robert has asked me not to read his bio since it's on the screen. So I let you read it, but I have to say a couple of things. One of the things is that Robert is one of the very few people whom I could go to for almost any aspect of validation that I needed any help with. right from emulation to post-silicon validation to formal methods, from microarchitecture to hardware to anything almost. In fact, he was famous for developing his very interesting scoping studies for a complex problem like validation at different areas in Intel. As a new researcher in industry, I was almost at sea when I started, and it was primarily his study and his analysis that helped me at least get a hold of navigating this problem. So I'll now let Robert speak. He has a slide that I'm going to share, but it's not in PowerPoint. So I'm going to stop this sharing and I'd start sharing his.
All right. Thank you, Sandip. Can I just confirm that you can hear me?
Yes.
Okay, excellent. So I want to start by saying something about abstraction. And I'll also keep my comments brief. Abstraction is really an effective tool. It helps us build complex systems. It helps us understand complex systems. It helps us develop and manage complex systems. But abstraction in a security context, especially in a hardware context, can be very tricky, because something that seems very minor at the very lowest levels of your hardware can end up punching through multiple layers of abstraction, all the way up to something that is application visible, or in a virtualization context, something that is visible or causes problems in isolation, for example, between guests. So with that theme, and you're going to hear a lot of echoes of what Kevin said, 4 ideas that from a practitioner's perspective will be quite familiar, but I want to talk about them in a security context, of course. And Sandip mentioned at the outset that we would have a variety of people consuming the panel, listening to the panel, right? People who are deep experts in security, some students who are just starting out. So I hope these ideas are helpful. First, correct functionality of a design is a precondition for security. So what I mean is that we've spent a lot of time thinking about security and security features, but validating just those features, and by the way, as Kevin said, everything he said I agree with. Validating those features, designing those features is difficult. We can't neglect the underlying functionality. And it goes back to my theme about abstraction. If the underlying functionality isn't correct, a lot of the assumptions that the security implementation makes may be violated. So we have to make sure that the design is correct in the first place. This has always been a difficult problem. It's even more difficult now. And I believe it's foundational to security. Secondly, Kevin also mentioned this, negative space is no longer a don't care. What do I mean? You have to think hard about what your design does with ill-formed or even illegal inputs. And you have to, the design needs to fail safely and securely. And what this means is that we need to specify and validate the behavior of a design for every input, not just the inputs that are, for example, if you're designing a processor, what does a legal program look like? What does a legal bus transaction look like, right? You have to think about what it does for an ill-formed input. This takes the validation problem that was already hard and makes it even harder. And I believe we actually have to think about specifying, designing, and validating the negative space in a way that we can comprehend it and work toward it. Next thought, and this is, if I were to say, what have I learned over my career to this point, and I'm still learning, but I think it's this: complexity costs a lot more than we think it does. One of the most exciting things for me about working in the computing industry has been the clever ideas that I've encountered along the way. Beginning in school, I remember how exciting it was to learn about microarchitecture and pipelining and the beginning of the out-of-order implementations for microprocessors. But there's an important piece to this, which is that the extra effort that it requires to think up and implement complexity isn't actually the cost. The cost is in verification and validation, making sure that all of the pieces of complexity work together correctly. That's very difficult to anticipate. And in some cases, you see almost what we would characterize as emergent behavior from those interactions. And there is often a lot of re-engineering around these surprises. So in unexpected interactions or corner cases, we end up re-engineering. This is all cost that has to be paid, but doesn't in the end contribute to new features or better performance or increased functionality. You're re-engineering what you thought you already had. So use complexity with great care. And finally, the basics are surprisingly effective. And again, Kevin mentioned many of these, but input validation, bounds checking, authenticating every access, building with defense in depth. Some of the basic principles about security are surprisingly effective. And very, very often when we see a security issue and we look at the root causes, there are several things, several of the basics that have been either overlooked or somehow have slipped through either the engineering or the tools. And so again, there's a lot of really advanced work happening in security that's critical and very important. But my appeal here is that we have to think about design basics, security basics, and manage complexity in a way that the complexity that we do add is fundamentally necessary for the problem that we're solving. Back to you, Sandip.
Thank you, Robert. Let me share my screen back. Okay. Our next panelist is Professor Sharad Malik from Princeton University. Sharad is a George von Ness Lothrop Professor of Engineering at Princeton. He has served as a director of multi-university gigascale systems research center. His research in functional timing analysis and propositional satisfiability has been widely used in industrial EDA tools. He has received several awards. I mentioned just a couple. He's had the DAC Award in 2013 for the most cited paper in the 50-year history of conference, the CAV Award in 2009, and the IEEE the A. Richard Newton Technical Impact Award in EDA in 2017, among many others. Again, as a personal note, I personally probably learned most or a whole lot of satisfiability and its applications from reading his papers. So it's an honor to have him here. So with that, I'll turn it to Sharad.
Great. Thank you. Thanks, Sandip. Again, just a very quick check. Can people hear me? If I can just get a thumbs up. Perfect.
Yes.
Great. Thank you. So basically, what the word that I'm picking up here on in the title is the future, and I will try and focus on two parts of the future, both the challenges part as well as where there are interesting solution approaches emerging. And I'll again focus on a couple of things in each to let us go a little bit deeper in this panel, if we may. So the first part that I'd like to focus on is, when we're looking at our systems today, there's an increasing amount of firmware that's getting shipped with the hardware. And the firmware is a very key component of our SoC systems. And also it's something that's opening up the attack surface for these SoCs. The number of hardware components that are now accessible through firmware is increasing dramatically. So that's the growth of various accelerators, compute engines, including security engines that's shown in the graph on the left. And then the picture on the right essentially shows how in an SoC, various IPs may contain their own firmware, and the importance of third-party IPs was raised by both Sandip and Kevin, and how these IPs may actually have firmware interacting with hardware modules and different IPs then interacting with each other through some on-chip interconnect. And this essentially, gives a fairly large attack surface for attackers to come in and go through this common NOC interface through their own IPs. So the the big challenge here is, how do we co-verify these firmware hardware interactions, especially across multiple IPs? And the big difficulty in this is that the differing levels of abstraction between the firmware, which really is at the software level, and the rest of the system, which is at the hardware level, at a much lower level of abstraction in terms of if you look at the state transition system. So, this was something that we'd been looking at for a while, actually in collaboration also with Intel. And the sort of idea that we started exploring was, how do we raise the level of abstraction for the entire system to the software level? And in particular, how do we represent the hardware using instructions just like the software is represented? And so we came up with this abstraction called an instruction level abstraction. I won't go into its details, but I just wanted to point out that essentially by using this, you can now model the entire system fairly accurately in terms of these interactions, but at a much higher level, which then lets you use both simulation-based as well as formal verification-based techniques. And we've had some good success with this, including in a collaborative project with Intel. So the next point that I want to raise here is, and this is a point that Robert also mentioned, is if we look at, so this is sort of more in the direction of, where our promising approach is. If we look at, what's really happening in terms of attacks and attack surfaces, then there's some common themes that start emerging. So one way to look at a lot of what's happening on the attack side is that we design our systems using layers of abstraction, the programming language, the hardware software interface such as the ISA and the MCM, the memory consistency model, and then the microarchitecture or the implementation abstraction layer, which then is the abstraction that the ISA sees and so on. And if we see how the attackers are actually formulating a large number of their attacks, they're utilizing information that's leaking across the layers of abstraction. I think Robert used the term, punching across all the way up to the application layer. And this is happening in many different ways. So for example, they may be in the layers of abstraction unspecified behavior, for example, how overflow is handled. And I think this may relate to the negative space reference that he made, and I think Kevin also brought this up in a slightly different way. So the attackers may use the fact that they know how certain unspecified behavior is implemented, such as overflow handling. They have information about data layout, which a layer of abstraction, if it was hard, should not be leaking. That how data is laid out should not be available at the programming language level. And given that this information is available, the attackers then use it in a variety of attacks, control flow attacks that, for example, come out of buffer overflow vulnerabilities. And then finally, again, information that should not be visible across layers of abstraction, such as resource sharing in caches, things that led to Spectre and Meltdown, which then essentially you can get information leakage through side channels, again, is something that attackers use. So the common theme across these different attack categories is what attackers are utilizing is information that's now visible across layers of abstraction, which should not have been visible had those layers of abstraction been perfect. And given this information that's leaking across these layers of abstraction, they now utilize information about and this information is leaking through individual information assets, and then essentially they're utilizing this to get hold of key security assets through confidentiality or integrity attacks. So sort of a uniform way to thinking about how we might be able to defend against a very large category of attacks is to strengthen and preserve these layers of abstraction. So one possibility, and this is a project that I've been involved in and was funded through the Darpa SITH program, is the design of a Morpheus processor, which aims to do this through essentially using the dual techniques of encryption and obfuscation. And the obfuscation is done through churning, that is a rapid change of key information assets such as pointer values, data location, etc. So I'll stop here, with these two big themes: increasing firmware and the need to raise level of abstraction to manage the security attacks because of firmware. And the second is, how through strengthening of the layers of abstraction, we can have some very broad security defenses against a very broad range of attacks. I'll stop here. Thank you.
Thank you, Sharad. Let me share that. Okay. Sorry, I went the other way. So next panelist is Janine Mckeown. He received his bachelor's degree from Cedarville University in 2009 and MS and PhD degrees from Ohio State in 2014 and 2015. His research at OSU included high-speed and interleaved data converters, low-power serial communications, and MM-wave IC design. Since 2017, he has been a research engineer with the AFRL, where he leads internal design efforts in hardware security and trusted microelectronic systems. He holds 2 patents and has authored more than 15 conference and journal publications. So Jamin, the floor is yours.
Thank you. Also, I put those dates in there just to emphasize that I'm the junior panel member here. So I'm going to keep this short. So as I said, I lead design efforts at AFRL in trusted and assured microelectronics. And really what we're getting after is something that's adjacent to security. It's not exactly the same thing. We're really caring about the integrity, the confidentiality, and the correct use of parts in DoD systems. And obviously, there's a lot of interplay between that space and the security space. And so hopefully I can give that kind of perspective here. In general, though, much of the infrastructure that we would need to guarantee integrity and confidentiality is also really critical for security. And obviously, that infrastructure has been built over decades and has done a phenomenal job of assuring the functional use of the electronics that we use every day. And those things, in many ways, to even speak against those different processes is heretical, because they've done such a good job of guaranteeing the complexity that we kind of use in our day-to-day life. But kind of because they target the functional nature of our circuits, as many of the panelists have already said, they kind of miss either areas of abstraction or between layers of abstraction. And so just by definition, just a functional evaluation of a circuit, I don't believe is sufficient to guarantee or even kind of get us towards a goal of a secure circuit. And so I think, you know, in my view, the common infrastructure that we're using for assurance, there are layers to be added, and I think we've seen a lot of those layers in the last couple of years even start to be attempted to be layered on. And I don't know, I'm really optimistic about that. In general, some of the stuff that some of the other panel members mentioned, I think are extremely important. Reference designs were mentioned, policies, metrics. On the policies front, I know MITRE and other people are putting out kind of demonstrations of hardware bugs or lists of hardware vulnerabilities, and I think those are going to be essential as we move forward. You know, borrowing a little bit from the software paradigm, where we say, hey, we know we have these known lists, and we're going to run regressions against these known issues on all of our hardware. And I think there's going to be we're going to see more and more of that in the future. The issue, though, is all of those kind of are predicated on having known issues. And if anything, the design space that we're going into and the environment that these systems are going into is in many ways unknown. The boundary of our systems is a little bit unknown, whether it's because of new firmware that's getting added or the hands that are actually going to be holding these things. And then it was also stated by the gentleman from Intel, the complexity that we're seeing. There are unknowns in there. I remember there was I have the quote here, so I don't misquote it, but there was a paper out of Google 2 years ago, and it was in reference to a specific hardware issue, but that's not important. But they made the statement that we've been trading security for performance and complexity all along, and we didn't even know it. And I think like that speaks to, in many ways, the hidden nature of the security vulnerabilities that we have to deal with. And so whether it's because of an unknown boundary or because of the complexity that we are introducing into the systems and obviously the performance and the time scale that we have, I think a posture of assumed vulnerability is going to be really important moving forward. And what I mean by that is, it's typically for a really complex system, like a plane. That's my go-to example. You kind of assume that I have a system, it's supposed to be providing this functionality, but what happens if it doesn't? What's my backup? And then if those two systems together don't provide the correct functionality, what's my backup from there? And I think having a layered approach to microelectronics is doable and has been done in many areas. But I think kind of having that mindset going forward when we're talking about security verification or assurance verification is going to be really important. Like, we're going to do everything we can. We're going to have policies and metrics and reference designs that we're going to use upfront to guarantee the most secure design that we can get with, you know, old and new verification tools. And then what happens, just assume that this thing will be broken. Assume someone's going to be enter into a place they're not supposed to. What then? What's my mitigation then? Because for software, you can patch it. And for hardware, you can't. You have to, in many ways, either reduce performance with software just to mitigate the hardware issue, or you have to throw it away. And so I think that's the posture that I'm looking to going forward. And I'm excited to see what the other panelists say. So, thanks.
Thank you, Jamin. Our next panelist is Keith Rebello. He's a program manager at Darpa, at the Microsystems Technology Office, where he leads research in hardware and supply chain security. He has led multiple programs, and he's leading multiple programs in Darpa. His 6th program is developing computer architectures to protect systems against the entire class of software-enabled hardware vulnerabilities. He ran Darpa's first bug bounty program, which was called Faked. His safeguards against hidden effects and anomalous Trojans in hardware. The Shrinkage Microsystems Exploration Program seeks to find supply chain implants. Prior to Darpa, Keith held technical leadership roles at Department of Defense, Johns Hopkins, Applied Physics Laboratory, and in industry. So with that, I would give the floor to Keith. Keith, you want me to share your slides? So then I am going to share his PDF.
That would be great. Thanks, Sandip.
Yeah, give me 1 second to share things back. You can see my slides.
Great.
Your slide.
Thank you. Yeah, so I wanted to look at this problem from a slightly different direction and talk about some of the challenges and opportunities looking at PC boards. So if you go to the next slide, please. Okay, so as motivation, I wanted to talk a little bit more about the supply chain. Sandip mentioned kind of the global aspect of the supply chain, and I think a lot of work and effort has been put in trying to, design and verify ICs, but not a lot of effort has been put in looking at kind of the board level aspects of things. And so Bunny Wang gave a really good talk at Blue Hat in 2019, and I encourage you to Google it. It's on the web. You can watch his talk where he put on the hat. If he was a nation state, how would he attack the supply chain? And he wouldn't attack it at kind of the IC level. There are many softer spots, which you can see here on the left of this slide, where someone could attack things. And in 2018, Bloomberg came out with the big hack article, which was never proven to have happened, but I think regardless, that is definitely kind of illustrates what could happen. And in that article, if you're not familiar, they had postulated that China had they had replaced passive components on server motherboards with active Trojans, and that allowed them to get access to servers that were in the data centers of many large hyperscalers that we're very familiar with. So if you could go to the next slide. And while that definitely makes things easier for our adversaries, it doesn't make things any easier for us defenders, right? There are a number of challenges when we look at the PC board problem or the electronic assembly problem. A big one is complexity. A server motherboard has thousands of components on it. Advanced boards these days have 10 plus different layers. We're using advanced technologies now when it comes to packaging and the development of our circuit boards. So we have package on package technology, and we have buried components, we have buried vias. These make it very challenging for us to actually access the circuitry to test it. We have a lot of different noise sources. So on the right of this slide, you can see two SSDs. So these are identical model numbers from the manufacturer, but you can notice some interesting things just looking at the big components, right, on these devices. So we have different SRAM suppliers. We have different flash memory suppliers. We have a different SSD controller chip. How do we tell if these are benign or malicious things? They can be running different firmware, software, the boards can have different revisions. We're currently in, I think we're all feeling it, experiencing the global semiconductor supply chain shortage. And, that is causing suppliers to respin boards and swap components just because they're not available. So there's, various things that increase our noise and make things very, very challenging. Another very important thing, I think, for this problem going forward is that, when we buy COTS components, we buy commercial hardware, they don't come with design information. And, oftentimes we don't have a golden sample. There's no golden reference. When I was talking with the Navy, they had mentioned that they had purchased two routers from a major manufacturer, and same identical model numbers. And just like this SSD problem, when they cracked them open, the motherboards were completely different inside, right? So just because you have a sample doesn't mean that you have a golden sample, right, that you can compare everything to. So I think, the bottom line is that this is an area ripe for research and advancement. There's been a lot of effort when it comes to EDA tools and verification tools on the integrated circuit side, but that same level of investment hasn't, for whatever reason, taken place when it comes to the circuit board side of things. And so I think that there are tremendous opportunities to explore in that space. Thank you.
Thank you, Keith. So this is the end of the position statements, and we would have an open Q&A session from now on. So I thought there are a couple of questions already on the chat. Please continue to put questions in the chat, and I will ask them for the benefit of the panelists, and they will answer. But I thought I'll kick it off with a question of my own. Just as a moderator, I might not have a chance to slide a question later. So one thing that when I was listening to all of your position statements, one thing that occurred to me is, what do we do about specification? We know, so Robert brought up these things that we have to consider the behavior of the input, the design on everything, and not just legal ones and so on. But we already know specification of a complex system is complex, and nobody is willing to really write it. And even if they wanted, they probably wouldn't. And now you are asking somebody, presumably, to do some specification, not just of legal things, but of illegal things and whatever else the design is going to essentially do in order for you to say security. How is that even possible in the sense, even in principle? Does it mean that the specification is the artifact itself? Is there anything that you can write as a simpler specification? When you brought up the question of abstraction, that's one side. The second side is that there are all these various kinds of formal languages and other things. And many of these things I think were brought up. I think Sharad brought up some things about hardware, firmware interfaces. But the question is, how do they work with, will this work with the regular current flow? And how will they be adopted? Will anybody adopt them in mainstream? If not, then today's security is purely reactive, right? You find a security problem, Spectre, yeah, everybody now goes after Spectre. You find some others, I'm sure they would go after that. And maybe you'd even extend specifications to do so. But what do you do about things that are not known? And how do you write specifications for that? I thought I'd bring this up because this seemed to be something everybody was saying, but not really this directly. So anyway, anybody wants to say, have any thoughts on this?
Sure. So I smiled as soon as you said specification, because that has been one of the biggest topics in practice in my experience in my career. Specifications are, everything you said about specifications is correct in my mind. They're tough to get a good specification and to remove ambiguity. So my observation is we do this in a couple of levels in practice, and I think even the answer to your question about how do we do this is probably similar. I believe that every bit of work that we put into specifications pays off multiple times downstream. Doesn't mean it's easy to convince everybody involved in the design process to do it. But we don't, and I'm a big believer in formal techniques and precise work and specifications, right? But just having the architects and designers at the beginning of a task thinking about, for example, the negative space and writing it in an English description is better than not having it. But even if you don't have that, if you make part of your validation engineering, if you make part of that task, understanding what has been specified and what hasn't been specified, often the validation engineer has to figure out what the specification is anyway, right? And so you could start with security validation. If you have funded security validation, or if you have, as part of your validation effort, you explicitly have security, you add to the validation task, think about the negative space. And it may be that the way you start is the validation task or the validation engineering first creates a specification of what they assume this negative space to be. But your comment is good, and I think that the more precise and the more complete the specification is, the more opportunities there are to examine the specification itself for weaknesses and to leverage the existence of that specification as we design and then check against the design.
Yeah, that's a very good point. Anybody else wants to weigh in on this? And we will get to the audience questions in a second.
I'll jump in for a quick second. I very much like what Robert said. I'm just going to pile on in addition to it. I think there's some important security basics to apply that can be applied to specifications as well, to include kind of a principle of minimal functionality, right? Least capability, minimal functionality. I think often we end up over provisioning all the way back to a specification phase for the purposes of reducing modification risk downstream. And I think that's kind of one good technique to bring to bear.
I'd also like to pile on a little bit to this. I agree completely with Robert and Kevin here. I think one of the challenges and issues, though, and I think it's a larger issue that goes back to something that Jamin had said about Google, that I've experienced a lot at Darpa trying to get our technology transitioned, is that, no one wants to pay for security. no one wants to pay for specifications. Better specifications are critical. They're, really important. But how do we get the community to adopt that mindset and go down that route? In the software space, it took kind of a presidential directive to get people to report out their SBOMs, right? Their software bill of materials, where pieces of software are coming from, who's making them. We don't have anything like that in the hardware space. And so, I view this specification problem or challenge in a similar light to just the overall security challenge of how do we get better security adopted? Because I think we know, best practices, and we have technologies that could help a lot, but people just don't want to adopt them because they simply don't want to pay for it.
Yeah, that's a good point. One of the issues might be who writes it and who consumes it. So okay, so let's go to the audience questions. The first question, Prabhuddha Chakraborty, he asked, what are your thoughts on different security challenges, specifically in edge devices and systems that are running on a simple hardware with minimal or no operating system? Anybody wants to take that?
I don't have a complete answer here, but I think that, especially on the edge and for simple systems, I think that having an assumption that it's suspect, or at least this should be validated before an answer is kind of fully brought into the system, I think is really important. I think that's going to be even more critical as we start to bring in sensor data for just everyday life, and we'll have machine learning operating on that, right? Like there's this idea that data coming in is an easy way into a system. And so I don't know, like for specific applications, it might be different, but I think having a confluence of information coming in. I know in a lot of, very important safety critical systems, they have voting, multiple systems have to be giving input. And I think just having the, like you said, for the specifications early on, just having it thought about early, I think is really good. And a lot of times for these really small, really simple, edge platforms, people don't think about, hey, this thing could get corrupted immediately, or as I build it, even we talked about the bill of materials problem, like this could get corrupted. So I think having that thought early on in the system is important.
Yeah, that's a very good point. I guess one reason for this question is that, well, if you are really just in a pure hardware sensor sensor connected hardware that directly communicates with clouds with no software, then you really cannot mitigate things later in field. So, because as I think one of you mentioned, hardware is kind of immutable at some point. So that's probably one of the reasons that this could be a different problem. I want to go to the second
Sandip,
question.
could I just add one quick thought to that?
Sure.
I agree completely, and I think that part of what Jamin's saying is this concept people have started to call zero trust, right? Mm-hmm. And it's not just authenticating every access. You have to decide as a system designer which parts of the system you can fundamentally trust. And we make assumptions about which part of the system we can trust because it may be under our control, but you have to think about which parts of the systems can you trust under different attack models, right? Including a physical attack. And so if you think about an edge device, the right posture is probably not to trust it or what it's telling you. And you have to do the same kind of input validation and authentication validation that you would do if you knew you were talking with a potentially hostile channel, right? And so I think it really does pay for us to think about trust in a mode where security's been compromised, because it changes the kind of authentication and checking that you do, even in your fundamental system design.
Yeah.
I'd like to make a comment as well on that. It's a little bit counterintuitive maybe, because you think about simple hardware, simple systems. Oh, well, it should be, a lot simpler to protect that. But oftentimes it's the opposite, right? Because as Sandip mentioned, these systems don't get updated. And so, one of the things that we've been talking about at Darpa for a while now is bringing the level of protections down deeper into the stack. So instead of trying to do our protections at the higher level, at the application level, at the software level, bringing them down into the firmware and the hardware level so that we can, kind of build a strong foundation for these types of systems that don't get updated as often, if ever. And so I think that's really important.
Yeah, that's probably very critical.
I'd like to just pile on one more thing. Yes to all that, yes and. I love the question because exactly as we were saying, the security verification challenge of an ed device is an astronomical challenge, in no small part because there's not the value proposition, the economic incentive to care much about security in edge devices, right? A lot of decisions about over-provisioning capability, about the degree of rigor by which we support verification in design and through operations are just not there, right? There's that out-the-door capability first model that ends up leaving a general purpose computer that's rather quite capable in every smart device in my house. And that fundamentally, I think, is an important security problem.
Mm-hmm. Yeah.
Yeah, I mean, it really goes back to what I was saying earlier. Nobody wants to pay for security, especially as the price of the device goes down. It's harder and harder, right, to add cost to it, add security.
So I want to go to the next question. This is probably a very fundamental question. Payman has asked it, and I think Patanjali as well. Is there a figure of merit to security? I mean, what is the criteria to say that a provided security is good enough? Anybody wants to take that?
Well, I can talk a little bit from the Darpa perspective. I think this is a great question. I think this is a challenge. This is something that we, the community, have not figured out yet. How do you measure security? It's really quite challenging. I can tell you what we did on SIF. So on our system security integration through hardware and firmware program, where we're trying to make cyber resilient processors that can be immune to software enabled hardware exploitation. We used a series of different techniques, right? So we used formal methods, right, to try and prove that the systems we are building are doing what they say they're going to do and nothing extra. That's challenging because that is, those proofs are only as good as your assumptions, right? And so if, you're basing those assumptions on specifications that are incomplete, that can lead to some challenges. And we found that to be challenging. One of my teams had a really super sharp team from MIT. And, they did something that I thought was crazy at the time. They built their processor in a formal language. So they used Coq to actually build their processor and then synthesize it. And, they were very sure that it was foolproof, right? The hardware was secure. We've mathematically proven it. And the second kind of approach that we use to measure security is our FET program. So I ran our first crowdsourced bug bounty program, and we took some of the hardware that we had developed on SIF, and we threw that up in the cloud to allow pretty much anyone in the world to come hack it, right? We had close to 600 people from around the globe, white hat hackers, security researchers. They spent over 13,000 hours banging on our hardware and stress testing it. And these were, hardware systems that were using SIF processors, but I think the interesting part was old janky software. So, old software that had known CVEs, so known exploits that could be thrown against them. And throughout that 3-month period that we ran FET, none of those exploits were able to be exploited. However, when we gave the researchers kind of exquisite access and allowed them to write their own programs to demonstrate that they could exploit one of the weaknesses that we claim protection for, they were able to break the MIT solution multiple times. And it turns out that they were, that solution had really great hardware, but that technology was implementing secure enclaves. And the way they were doing that, they were managing those enclaves with a piece of firmware that sat in between the hardware and the software. And that piece of firmware wasn't formally verified. And that is what the attackers attacked. And they were able to break that and extract all the secret key information in the system and totally own the entire system. So, I think that resonated with me, that, the strength of the mathematical proofs are really, again, only as good as the assumptions that you make in those, specifications that you build everything on top of. So formal, we talked about, crowdsourcing. The other thing that we did was we did independent security evaluations with transition partners and corporations. And so we did an effort with Microsoft Research where they examined our hardware and did a thorough evaluation of it. So those are the 3 techniques we used on SIP, but there is no, I guess I should mention another thing that we did. We did on the program develop a synthetic security benchmarking tool. So we took about 130 different CWEs from the MITRE database that focused on hardware, and we built a software program to exercise and probe those. So, similar to a performance benchmark that you can run on your computer, we now have a CWE kind of benchmark that we can run on a computer system and architecture to see how well does it protect against a variety of different weaknesses. But there's no overall standard and way to measure security. It's still, in my mind, a research problem, one that we're still trying to explore at Darpa. Actually, in a couple of weeks at ERI, at the Electronics Resurgence Initiative, I'm going to be hosting a workshop with experts from the NSA, from Qualcomm, from Microsoft, and the ICS community to look at how, the enterprise community, how the handset community, how the ICS community, how the government looks at security, how we measure security, and what kind of are the best practices and ways to kind of come up with a way to measure security. Sorry for rambling on there.
So if I may just add a little bit to that. So one of the SIP projects that was funded through Keith's program was this Morpheus processor, which was led by my collaborator Todd Austin at Michigan. So as part of that, sort of one of our sort of observations and which led to the solution approaches, which is what I was trying to touch on in the last slide, was that there is this pyramid of where you have information assets that lead to vulnerabilities that lead to exploits or attacks. So if you look at this pyramid, the number of information assets that get exploited is relatively few. That's relatively small. These lead to a much larger number of vulnerabilities, which of course, we have ways of documenting those, covering those as we discover them, and then which lead to exploits and attacks. And then the defenses are sort of focusing around, how do we eliminate these vulnerabilities, or how do we defend against these vulnerabilities? So I think part of looking at measures and metrics is the root of all of this is information, information assets, and information assets include things like timing information that may be an information asset that an attacker may get through side channels. So if we document those and then in our solutions talk about how well are we covering against known information assets, which is a level below the vulnerabilities, I think there's some value there, because this is a relatively smaller set, And it also gets to one of the other questions that was coming up in the chat here, which is, how, as academic researchers, how do we think of attack surfaces? So I think the root of a lot of things comes around information assets that are visible to attackers that also connect to one of the things I was saying, and Robert mentioned, which go across layers of abstraction, which normal programmers and normal hardware designers are not thinking about, but this is information that's leaking and attackers are exploiting. So if we can focus on around information assets and make that one of the metrics that, what are the information assets that we are protecting against, I think there's value in that.
Yeah, that's a great point. I think a lot of times when we think about figures of merit, we kind of harken back to circuits and their performance, and that's kind of where that comes from. And I think that for a lot of these challenges, a figure of merit isn't good, a good way of thinking about it. Some it is, but some it's not. Like, does this key lead to the bus, right? That's a yes or no question. There's no figure of merit there, right? And so for figures of merit, there have to be kind of analog, continuous measurements that are taking place. And then there needs to be some type of, like, I don't know, competition to get better. And so for things like side channel attacks, I've started to see that just a little bit in the academic publications, where people are starting to get to, hey, I have a good way of reducing my power side channels. Oh, I have a better way because it took more traces. Well, eventually, my hope is that coalesces around, I can measure the amount of information that's leaking out of my product. And that level of information, I'm able to reduce it. And I'm just using basic communications theory or information theory to have some kind of understanding of the mathematical amount of information that is available. And I'm reducing that. For some of these things, though, I think it's just specification. It's, does this happen or does it not? And then, am I able to anticipate all the ways that it could happen? And in that way, it's ad hoc. And I don't know a good way around some of those ad hoc ways of defending.
Maybe I should just say one little thing here. As a graduate student transitioning to industrial research, every time I came up with a research idea, my manager asked, what is your metric? And I have to say that every time they asked me, I was like mad at them. Like, I didn't know what they're asking for. But eventually I learned that that's really critical, because then there was a time when there was a banner in a cafeteria that says, congratulations to the team for finishing 10 trillion tests. And somebody asked, I don't remember who, does it mean they have done enough, or does it mean that they have not done too much, or does it mean that they have done nothing? We had no idea. And that was when it struck me, yes, the manager is asking me and I'm mad at him, but maybe there is a reason he is asking, and we really need to think through this. But the point is that sometimes as researchers, we probably don't consider matrix the same way, and that is probably very critical for sort of adoption or usefulness of any kind of a solution, particularly a validation solution. I want to maybe go to another question. We are sort of slowly getting towards close. So one Nimisha asked, like, since an attacker can try novel approaches, how can we anticipate security vulnerabilities? Anybody wants to take that? How do we do anything against unknown attacks is probably the question. And so maybe this is also related
I'll just repeat a little bit of what I said in the last one. So, so in this sort of reverse pyramid, the vulnerabilities all stem from information assets. So let's focus on the information assets, even before the vulnerabilities. And information assets are of the form, data layout, how is data laid out? Timing as an information asset. So what are the side channels that could potentially leak timing information? Information assets such as how certain undefined behavior in programming languages is implemented, because programmer writes a certain program not fully aware of how certain undefined behavior will actually get implemented by the compiler. But the attacker figures these things out through either documentation or probing, just testing systems and seeing, okay, so what's going on here? And these then lead to vulnerabilities, which then lead to exploits and attacks. So I would encourage people to start thinking about information assets as being the root of where things start, and use that to either protect directly against that information leaking, or think about vulnerabilities that may emanate from them.
Anybody else wants?
Yeah, to add to
weigh in?
that, I think that's great. Think about where your information is, what your information assets are, right? And let's take the question at its very nature. What do I do about unanticipated attacks? So and in fact, let's think about what do we do about the attacks that we won't be able to anticipate, right? So there's one implication in the question, which is if we think hard enough, we'll be able to anticipate it. And sometimes we can, but there's also the set of attacks that we can't. And then I think it's back to the first principles. Do what we know how to do and do it well, and you will reduce your attack surface in general. It doesn't mean that there isn't a novel attack, that you'll prevent all novel attacks, but you'll prevent many. The other thing that I would add to this, and we haven't talked about this much today, but think about resilience and recovery. So if there is something that happens to your system, regardless of hardware or software, what are your mitigation options? It can be very difficult in both worlds, right? Particularly in hardware. But what are your mitigation options? Are they general enough? And do you have enough? Do you have enough of them? Right? Is there enough capacity for if you figure out a mitigation option, do you have enough capacity to engineer everything that's going to come along? And you have to think about lifetime. Some of these systems are going to be around for a long time. So I think it's a great question. And I think that there's a lot of creative work we can do to think about attacks that haven't been thought of yet. I also think we have to engineer our systems for the inevitable attacks that we haven't thought about.
Thanks, Robert. We have, maybe we can slip in one more question. It's amazing that we are almost over in time at this time. We have about 10 minutes, and I'd like to have about 7-8 minutes for closing remarks. So this is probably the last question before we get to that. So this is from Stephen Baca. He says that abstraction and modularity seem necessary to manage the sheer complexity, but these abstractions reach well beyond just the IC and PCB level to software and mechanical levels. Given that it is these specific abstractions that contribute to many security issues, can we really address system security problems strictly through these means? How do we bring in computer science and mechanical engineering and other fields to address these issues holistically? Anybody wants to take that?
I'll keep it short so other people can answer too. I completely agree, and I have two points and two kind of examples. So yes, as an electrical engineer or a computer engineer, we have kind of a box that we have to work within, and I think security specification at a system level, not just mechanical engineering or computer science, but at a system level, and understanding like parts of the system that may experience more vulnerabilities and less, and having that understanding rolled into kind of graceful system failure is really good. Like when an engine falls off a plane, it can't just crash, right? You have to have like enough redundancy and enough, whether they're edge sensors or enough compute, or I don't know, even a graceful way of recovering from information theft. Like if I have a key leak, how do I deal with that at a system level? So I think having an understanding at a system level is important, and then those will get flowed down. The other direction flowing up, I think the Air Force has put a lot of effort into this recently, as have some major industry partners like Boeing and Airbus and others, on how do we flow up models so that system level people can actually interact more functionally with what's happening at the IC level. Typically, it's a specification that gets passed up or passed down, and then a very abstracted model gets passed up, and that's maybe it's a spreadsheet, and that's it. And so having, with our compute power that we've got now, like having ability to send models up, these may never in our lifetime get to the place where they're fully functional, but having some semblance of interactions between software and hardware, let's say, passing up to a system level, I think are going to be really important.
Okay, so I think we have 6 more minutes, so I'd like to get to a closing statement. So I'd like each panelist to give like a 30 seconds to 45 seconds, no more than a minute, of closing statement on what you think about the problem and the panel, and as a summary. So I will start with Kevin.
Okay, I'm going to leave with a mental model that I found sometimes valuable. It's not a panacea, but sometimes it's valuable, is to think about security and security verification processes in kind of a control theory perspective. We're trying to manage a system in a state space where it's security safe versus security unsafe. And we're trying to provide feedback to control the system into that place. And I want to connect that to this kind of prior question about, what can we do in terms of managing complexity through abstraction and modularity? I think if you look at it as a control system, and we're asking the question, what kind of feedback can we provide continuously in the design process and operations through decommissioning, especially of certain assets? What are the mechanisms by which we can nudge things either through best practices and first principles or through important new techniques and breakthroughs? How can we manage emergent vulnerabilities that, in the realm of things that were unanticipated or a consequence of our complex design? I think that's a valuable lens, a valuable way to think about the problem. And I just kind of want to share that and encourage the broader community to try to look for inspiration on the security problems from other disciplines, to include control theory.
Thanks, Kevin. Robert?
Thanks. I really enjoy these kinds of events. I learn a lot, and I learned a lot today. I think my closing thought is I'm going to talk about complexity again. Respect complexity. I'm not saying to avoid complexity, because that's the nature of the systems that we build. They have to be complex, but respect it and understand that just because you can build it doesn't mean it's a good idea, right? I'm riffing on a common quote from pop culture, but respect complexity and think about the implications of complexity and the long-term costs of complexity and what that means for security.
Thanks, Robert. Sharad?
Pay attention to abstractions. Abstractions are really key to tame complexity, what Rob brought up, in terms of, making the problem manageable, because you do want to abstract away details that are not relevant to, what you want to check at any level. At the same time, don't abstract away information that an attacker may actually have access to and can utilize. I mean, for example, in our systems, when we abstract, we are typically abstracting away timing information. We are not exposing, the information about timing of certain operations that attackers have. And this gets back to, the example. It's not directly the example, but the point that Keith was making earlier on is, when you're modeling, the assumptions that you're making are, your correctness proofs, etc., are only, correct as far as your assumptions are. So get your abstractions right. If an attacker can see some information, make sure your abstraction has it and it's part of your reasoning.
Thanks, Sharad. Jamin?
Yeah, since this is a CAD panel, I think I'll talk about CAD just a little bit. I think that taking a play out of someone else's playbook here on the software side is having and updating canonical sets of hardware vulnerabilities that we can run regressions against. I know that's easier said than done, because there can be, they have to be kind of formed into a way that your system can understand. It's not gonna be like, oh, hey, this one attack, I should just run it. It's not gonna work like that. But I think working towards having like canonical sets of issues that we can say, yes, we have checked that, and there's kind of a standard way of checking that, I think that would be beneficial. And then just as a way of thinking, assuming that vulnerabilities are going to happen. I think that's, usually systems who anticipate vulnerabilities are able to obviate them. Like, hey, this thing we have to worry about. They typically do a good job thinking about it because they're engineers and they're focusing on a problem. I think just bringing that mindset in and saying, hey, this thing can get cracked. Let me think about that a little bit up front. I think it's hugely important.
Thanks, Jamin. Keith?
Thanks for having me. I really enjoyed the discussions. I think I'd like to leave with, this is really hard. I think that was something that came across in spades during the discussion. Security is hard. it's challenging. These are, really, really complicated systems that we're building. As Robert said, there's lots of complexity here. But don't give up hope. I think, some of the things that, like what Sharad said about the pyramid, right, that we found that to be very, very true. That, it turns out that there are a small number of very critical weaknesses that you should pay attention to. And if you do that, you can really reduce the attack surface a great deal. And it's a kind of a compounding problem because, a lot of the exploits that people throw today are actually chains of multiple weaknesses, right, that need to be exploited in order for them to achieve their end goal. So if you can break one of those links in the chain, you can stop the attack from happening. And so if you're smart about, what you're going to focus on and protect against, you can have a tremendous impact. And we've seen that on the SIF program. So don't give up hope. I think there's a lot that can be done in the security space.
Thank you, Keith. So this is the end of the discussion. So I really enjoyed this panel. This was very interesting. Maybe there has been a little bit too much of agreement of everybody. There was not maybe as much any fight at all. Everybody was agreeing with everybody else, but that's kind of the nature of the topic, I guess. I was really hoping somebody would say, I don't agree with you, but nobody did. Anyhow, yeah, you want to have any closing remarks on the next set of things or any announcement?
No, I would thank all the panelists, and I hope everyone can join our webinars in the future.
Okay.
Thanks.
Thank you all. This was great. Thanks to all the panelists and thanks to the audience for the questions. And we will see you in the next webinar in November, I think. Thanks. Bye.